Hello friends, and welcome to a session on progressions. Today we will learn about geometric progressions. This is the outline of the video that we will follow up. We will see the definition of a GP, nth term of a GP, sum of GP, geometric mean, corresponding terms, properties of GP, inserting n terms between two numbers, and then solve some examples. So, a series in which each preceding term is formed by multiplying it by a constant factor is called a geometric progressions or a GP. The constant factor is called the common ratio and is formed by dividing any number by the term which precedes it. Which in simpler one, if we have a sequence a1, a2, a3 up to an, then the ratio of two consecutive terms is always constant. That's what the definition is of GP is. So let's see how to find the nth term of an AP. We have in a general form of a GP with n terms as A, AR square, AR raised to n minus 1, where A is the first term and R is the common ratio. If we look at this thing clearly, we can see that AR square is the third term, while the power of R is 2. AR is the second term, while the power of R is 1. So it is always less by 1 by the number of the term. So to derive the general term of a GP, Tn can be found as A into R raised to n minus 1. Let's see how we can find the sum of a GP. Sum of first n terms of GP is given as Sn is equal to A into R raised to n minus 1 upon R minus 1 when R is greater than 1. When R is less than 1, it is given by A into 1 minus R raised to n upon 1 minus R, and when R is equal to 1, it is simply n times the first term. Well, there is another sum that is important in GP, that is the sum of infinite GP. If a GP has infinite terms and the common ratio lies between minus 1 and 1, then the sum of infinite GP is given as A upon 1 minus R. We will see how to solve problems on this kind of infinite GP and how to find sum of this sort. Let's see what we mean by geometric mean. When three numbers A, B, C are in GP, then we know that the common ratio of two consecutive terms is equal. So B by A is equal to C by B, which gives us B square is equal to AC, or B is equal to root of AC. Here the middle term B is called as the geometric mean of A and C. Let's see an important concept of corresponding terms. Consider a GP given as 1, 3, 9, 27, 81, 243, 729 and 2187. Here if we look closely, the product of the first and the last term is obtained as 2187. But it is also the product of second and the second last term, third and the third last term, and fourth and fourth last term also. So here the product of first and last term is equal to the product of the second and second last term, and so on. So we can say that A1 into An is equal to A2 into An minus 1, that is second term into second last term, is equal to third term into third last term, and so on. This pair of terms is called as corresponding pairs or corresponding terms. Now let's see how we can insert n different terms between two numbers such that the series is still in a GP. So let us consider two numbers as A and B, between which we have to insert n different means. Thus the series will become A, G1, G2, G3 up to Gn and B. In this case, after adding n geometric mean, we get B as the n plus second term. So we will use the nth term formula for b as a raised to a into r raised to n plus 1 and get r as b by a raised to 1 by n plus 1. Once we get the value of r, we have to simply multiply this r with a to get the next term. Then again multiply r with g1 to get the next term, and so on to get all the geometric means. Now let's see some properties of GP. If all terms of a GP are multiplied with k or divided with k, the resultant series will also be a GP, but the common ratio will not change. It will remain the same. So if a GP is taken as 2, 4, 8, 16, 32, here clearly the common ratio is of 2. Alright. So if we multiply this series by 3, then the resultant series will be 6, 12, 18, 42. If we see at the common ratio here, it is still 2. So the common ratio will not change. Again, the second property says that in a GP, the product of terms equidistant from the beginning and end is always same and equal to the product of first and last term. We have seen that this is the property of the corresponding terms, where the product of first and last term is equal to product of second and the second last term, and so on. Now let's solve some examples on geometric progressions. Find the sum of the geometric series given as 2, 6, 18, 54, and there are 6 terms. So give this problem a try and then we will solve the problem. Okay, let's solve the problem. Now clearly we have few things over here, as 2 as the first term. The common ratio we can derive 6 by 2 as 3, and the number of terms as 6. So we can see that we have a is equal to 2, r is equal to 3, and n is equal to 6. So we can simply use the formula for Sn as a raised to a into 1 minus r raised to n upon 1 minus r, which gives us the final answer as 728. Okay, give this problem a try. The inventor of the chessboard suggested a reward of 1 grain of weight for the first square, 2 grains for the second, 4 grains for the third, and so on, doubling the number of grains for subsequent squares. How many grains would have to be given to inventor? Okay, let's solve the problem. Now here we can see this is a case of geometric progression where for every consecutive square, the number of grains which is being given is doubled. So clearly we have 1 as the first term, the ratio as 2, because for every consecutive square the number of grains which is being received is double. The common ratio should be 2, and there are 64 terms. So applying the sum of GP for n terms, we get the answer as 2 raised to 64 minus 1. Now solve this problem on infinite GP, sum of infinite GP. Okay, let's solve the problem. Now here we are supposed to find the sum of infinity of the geometric progressions given as 1, 1 by 3, 1 by 9, and so on. Here clearly the first term is a, that is 1, and the common ratio is 1 by 3. Alright, so we can use the formula for infinite GP as a upon 1 minus r, where a is 1 and r is 1 by 3, which gives us the answer as 3 by 2. Now solve this problem. In this problem we are supposed to insert 5 geometric means between 1 and 64. So give this problem a try and then we'll solve the problem. Okay, let's solve the problem. Now the series will become as, after inserting 5 geometric means, the series will become as 1 G1 G2 G3 G4 G5 and 64. So clearly 64 would be the 7th term. So 64 would be a into r raised to 7 minus 1, that is 1 into 7 r raised to 6. So clearly r comes out to be 2. So if we go on multiplying the first term, that is a, by 2, we get the first geometric mean as 2, then the second geometric mean as 4, the third as 8, fourth as 16, and the fifth as 32, and the seventh term would be 64. So clearly the series will become 1, 2, 4, 8, 16, 32 and 64. So we have seen that geometric progression is quite an easier topic with few concepts, and you can easily expect one question in the examination on geometric progressions. Thank you.